Euler's equation for fluid flow, and from Euler's equation we may derive Bernoulli's equation. Okay, so first of all, thank you for my last video on thin cylinder, great response, and thank you. And now this Euler's equation. For Euler's equation we may have some of the consideration, as the fluid element is a incompressible fluid, and the fluid is of steady flow, very much important during the derivation we may come across. And now for Euler's equation, firstly we have to consider an fluid element. This is our fluid element. This is of ds length. This has an area of dA. Okay, and now this is a little bit in an angular. You can say this is an angle inclination, something like this. So this is x, this is y, and this is s direction, not in x and y. This is s a little bit. So I'm write it like this, s direction. Now we may now calculate the pressure, pressure force which is acting on this element. So A, B, C, D. Okay. Just now this pressure force which is acting on this fluid element is like this, and if the self weight of this element, weight rho G dA ds, and this is acting vertically downwards, and this is an inclination of angle theta with the horizontal, with the vertical you can see. Now the pressure force which is acting on from this direction is P into dA. P is the pressure force intensity, and dA is the area of the fluid element, and pressure into area equals to force, as you know, as everybody knows. So now from in this direction, the force which is acting is P plus del P by del S into ds into dA. Don't get mug it up, I may explain it. Now see, this is our, first of all, the fluid element. Okay, ds length, and pressure which is acting on this element per unit length. Suppose this element is divided into, again which is divided into some of the few elements, and at each small parts the pressure force which is acting dP by ds. Okay, dP is the pressure intensity which is acting on del S distances, and in each element del P by del S, del P by del S, del P by del S. So this whole, okay, this may become as del P by del S into ds, the whole length. And we know that from here this P into dA, already the pressure force P is acting, hence it is added with a force of P, pressure P, pressure intensity, and this whole into multiplied by dA, which gives the pressure intensity into area. This is the force, so here pressure intensity into area. This section, I think this may get a little bit easy to understand. And okay, now we may calculate the net force which is acting on this element, and this is something like this, P into dA, which is acting like this. And here the sign convention are, we are taking the upward direction in S direction as positive, downward as negative, minus P plus del P by del S into ds into dA. We have just now derived that how this came. And now the weight which is acting on the fluid element on ds direction, this is like this, rho G dA ds into cos theta. And how this came? This is rho, the density of the fluid element, g is the gravity, dA is the area of the element, and ds is the length of the element. Very simple. When we are talking about the mass, we may remove the gravity. So simple. And it is acting on cos theta component, and this whole is equals to the force. Force is the mass into acceleration. Mass into acceleration. Mass here is rho dA ds. Okay. So when we open this brackets, and we may get something equation in the form of minus dp by dA minus del p by del s into ds into dA minus rho g dA ds cos theta equals to rho dA ds. Yes, this gets cancelled, and we may dA ds dA ds dA ds. Okay, we have a look at this, and this get cancelled, discount. Okay, and this equation will become as del p by del s plus rho g cos theta plus rho into as equals to 0. The negative which is taken to this side, and this equation is formed. Now here two unknowns, cos theta and as. So here is the theta. This is theta, this is ds, and this is dz. Dz is the height of the fluid element from the datum line. Okay, so here we get cos theta equals to base upon hypotenuse. Base is dz, hypotenuse is ds. Okay, and acceleration everybody knows, dv by dt. Okay, and v is the function of s and t. So we may write it here as as equals to dv by ds into ds by dt plus dv by dt. This is the formula you may get from any of the mathematical books. When the function is dependent on other two variables, then this is the formula. And now in this question, okay, this dv by dt, this is equals to 0. Why? This is in steady flow. We know in steady flow the change in velocity with respect to time is 0. Okay, so this term gets 0, and as becomes ds by dt equals to velocity, v dv by ds. Okay, so we got the value of acceleration as, we got the velocity of cos theta. So we may just put it here, del p by del s plus rho g cos theta is dz by ds plus rho v dv by ds equals to 0. Okay, now let's see this. We have got, okay, now one more thing, we may change del to d, that is from partial differential to complete differential with respect to pressure intensity on dz. Okay, now we have ds, so this cuts dv plus rho g dz plus v dv. We may replace it over here. Okay, this is equals to 0. So this is Euler's equation. ds has been removed and g has been divided in the whole equation. We got the Euler's equation. Now on integrating Euler's equation, we may get Bernoulli's equation. So this is like this, dp by rho plus g dz plus integration v dv equals to 0. Oh sorry, on integration we get a constant of 0. So p by rho plus gz plus v square by 2 equals to constant. So p by rho into g, we have divided the whole equation by gravity, g is equals to constant. Simple. We have got the Bernoulli's equation. Thank you.